Hello everyone, this is Dharmveer sir here. So today we are going to start the chapter 5 of grade 11 maths, which is complex numbers. Complex number, we all have learned about real numbers, and so this is a very new topic for all of us, that what are complex number, what are their different properties. So in this video we are going to discuss about complex numbers and their properties. Okay, so let's start. So what is a complex number? So a number of the form a plus ib, a number that can be written in the form of a plus ib, where a and b are some real numbers and I is equal to under root of minus 1. Under root of minus 1, I is called iota. Okay, I is your iota. It's called a complex number. So if we can write any number in the form of a plus ib, then that number is called a complex numbers. So a plus ib is the standard form. Now if z, the complex number, is a plus ib, then the a is called the real part of z, written as rez, and b is called the imaginary part of z, that is imz. Okay? I is equal to, we know that I is equal to under root of minus 1. So I square is what? Squaring both sides, we get I square equals to minus 1. So I cube is will be equal to minus I, and I power 4 is equal to 1. Similarly we have different powers of I, and 1 upon I is equal to minus I. Remember these points, these will be useful when you solve the sums. Okay, so pause and note down these important points. Now two complex numbers z1 and z2 are said to be equal if their real parts are equal to each other and imaginary parts are equal to each other. That is, if z1 is equal to a plus ib and z2 is equal to c plus id, then they will be equal if a is equal to c and b is equal to d. Now if you have two complex number z1 and z2, then their addition, that is z1 plus z2, is the addition of their real parts plus I into addition of their imaginary parts. That is, if z1 is equal to a plus ib and z2 is equal to c plus id, then z1 plus z2 will be equal to a plus c plus I into b plus d. Clear? So pause and note down these points. Now addition of complex number follows the following properties. The sum of two complex number is again a complex number. Clear? The set of complex number is closed. That is, the addition of complex number follows closure property. That is, if you add two complex number, you will get a complex numbers. The addition of complex number follows additive property. That is, z1 plus z2 will be equal to z2 plus z1. The addition of complex number follows associative property. That is, z1 plus z2 plus z3 can be done in any order. Now for any complex number x z equal to x plus iy, there exists 0, which can be written as 0 plus I0, and if you add z plus 0, you will get z. So this 0 plus I0 is the additive identity for any complex number. Now for any complex number z equals to x plus iy, there exists some complex number minus z, which will be equal to minus a minus ib, such that z plus minus z will be equals to 0. So that minus z is called the additive inverse of z, or z will be called the additive inverse of minus z. Clear? So pause and note down these important properties. Now next we have multiplication of complex numbers. So let z1 equals to a plus ib and z2 equals to c plus id. Then z1 into z2, that is the multiplication of these two complex number, will be equal to ac minus bd plus I into ad plus bc. Okay, if you multiply two complex numbers, you will get like ac minus bd plus I into ad plus bc. Now the multiplication of complex number also follows some properties, that if you multiply two complex numbers, then the result is also a complex number. That is, the multiplication of complex number follows closure law or closure property. Multiplication of complex number is commutative. That is, if you multiply z1 into z2 or multiply z2 into z1, the product is going to remain same. Multiplication of complex numbers follows associative property. That is, you can multiply z1, z2, z3, that is three complex number in any order, the result will be same. For any complex number z equals to x plus iv, there will exist another complex number 1 plus 0i. If you multiply these two, z into 1, both will be equal, or 1 into z, both will be equal to z. So this 1 that is 1 plus 0 I will be the identity element for the multiplication of complex number. And for any non-zero complex number z equals to x plus iy, there exists another complex number 1 upon z such that z into 1 upon z is equal to 1 upon z into z will be equal to the multiplicative identity, that is 1. And the multiplicative inverse of a plus ib, that is 1 upon a minus a plus ib, will be equal to a minus ib upon a square plus b square. Clear? Remember this point. And for any three complex numbers z1, z2, z3, so z1 multiplied by z2 plus z3 will be equal to z1 into z2 plus z1 into z3. That is, the multiplication follows the distributive property. Okay, so pause and note down these properties of multiplication of complex numbers. Coming to conjugate of a complex number. Now we have a complex number z equals to a plus ib. Then if we change the sign of imaginary part, then the complex number is called the conjugate of the given complex number. That is, if z equals to a plus ib, then its conjugate denoted by z bar will be equal to a minus ib. Simply change the sign of I. If it is plus I, it will be minus I, and if it is minus I, it will be plus I. So additive inverse of z is minus a minus ib, but the conjugate of z is a minus ib. Don't mix these 2 points. Okay, additive inverse is different and conjugate is different. Now we have the following properties of conjugate. That is, if we have z bar ka bar, it is conjugate's conjugate, then it will be equal to z. Now z plus z bar equals to 2 times of real z, and z minus z bar is equal to 2 times of I into imaginary z. Z is equal to z bar if z is purely real, there is no imaginary part. Z plus z bar equals to 0 implies that z is purely imaginary, there is no real part. Z into z bar will be equal to real z whole square plus imaginary z whole square. And z1 plus z2 bar is equal to z1 bar plus z2 bar. z1 minus z2 bar is equal to z1 bar minus z2 bar. Product is z1 into z2 bar is equal to z1 bar into z2 bar, and z1 upon z2 whole bar is equal to z1 bar upon z2 bar. You can take individual bars for addition, subtraction, multiplication or division. Clear? So pause and note down these important properties. Moving to next, modulus of a complex number. So let z equals to a plus I be a complex number. Then the modulus of z denoted by mod z is equal to under root of a square plus b square. That is the sum of the squares of the real and imaginary parts taken under root. Clear? So if z equals to a plus ib, then the modulus denoted by mod z equals to under root a square plus b square. Now we have the following properties for the modulus of a complex number. Modulus of z is equal to 0 implies that z will be equal to 0. That is, real part of the z is 0 and imaginary part of the z is also 0. Mod z will be equal to modulus of z bar, that is conjugate's bar, and this will be equal to minus modulus z. Modulus of minus z. Minus of modulus z is always less or equal to real part of z, less or equal to modulus z, and minus modulus z is less or equal to imaginary z, less or equal to modulus z. If you multiply z into z bar, you get modulus z square. That is, modulus of z square is equal to modulus of z bar square. Modulus z1 into z2 is equal to modulus z1 into modulus z2. Division, that is modulus z1 upon z2 is equal to modulus z1 upon modulus z2. Then addition, whole square, modulus z1 plus modulus z2 square is equal to mod z1 square plus mod z2 square plus 2 real z1 into z2 bar, and modulus z1 minus z2 bar whole square equals to mod z1 square plus mod z2 square minus 2 real z1 z2 bar. Modulus z1 plus z2 is less or equal to modulus z1 plus modulus z2. Modulus of z1 minus z2 is greater or equal to modulus z1 minus modulus z2. And modulus a z1 minus b z2 whole square plus modulus b z1 plus a z2 whole square will be equal to a square plus b square multiplied by modulus z1 square plus modulus z2 square. Or in simpler form, we can say that modulus of z1 minus z2 whole square plus modulus of z1 plus z2 whole square will be equal to 2 times of mod z1 square plus mod z2 square. Clear? So note down the definition of modulus and the properties of modulus. So let's start exercise 5.1. And the question 1 is, express the complex number in the form of a plus ib. Here we have 5i multiplied by minus 3 upon 5i. So multiplying these two, you get 5 multiplied by minus 3 upon 5 into I is I square. So we get minus 3 into minus 1. Why minus 1? Because I square is equal to minus 1. So this becomes 3. So we can write this as 3 plus I0 because we need to write the answer in the form of a plus ib. So here a is equal to 3 and b is equal to 0. Clear? So pause and note down the solution. Next we have I power 9 plus I power 19. We have to write this in the form of a plus ib. Now I power 9 can be written as I power 8 into I, and I power 19 can be written as I power 16 into I power 3. So I power 8 is equal to what? I power 4 square I plus I power 4 I cube, which is equal to 1. Why? Because I power 4 is equal to 1. So this is written as I minus I, because 1 square is 1 and 1 power 4 is 1. So we are left with I minus I, which is equal to 0. But we need to write this in the form of a plus ib. So writing this as 0 plus 0i, where a is equal to 0 and b is equal to 0. Clear? So pause and note down the solution. Next we have question 4. Express the complex number in the form of a plus ib, and the number is 3 into 7 plus i7 plus I into 7 plus i7. So opening the bracket, we have 21 plus 21i plus 7i plus 7i square, and since I square equals to 1, we get 21 plus 28i minus 7, which is equal to 14 plus 28i. So here we have the form of a plus ib, where a is equal to 14 and b is equal to 28. Clear? So pause and note down the solution. Moving to question 7. Express the complex number in the form of a plus ib, and the number is 1 upon 3 plus I into 7 upon 3 plus 4 plus I 1 upon 3 minus 4 upon 3 plus I. So opening the bracket, we get 1 upon 3 plus 7 upon 3i plus 4 plus 1 upon 3i plus 4 upon 3 minus I. Done. So we get 1 upon 3 plus 4 plus 7 upon 3 plus 1 upon 3 multiplied by I plus 4 upon 3 minus I, which is equal to 13 upon 3 plus 8 upon 3i plus 4 upon 3 minus I. So taking the real and imaginary, we get 13 upon 3 plus 4 upon 3 plus 8 upon 3 minus 1 into I, which is equal to 17 upon 3 plus 5 upon 3 into I, which is the required form of a plus ib, where a is equal to 17 upon 3 and b is equal to 5 by 3. Clear? So pause and note down the solution. Next we have question 8. Express the complex number in the form of a plus ib, and the number is 1 minus I power 4. So 1 minus I power 4 can be written as 1 minus I whole square ka whole square, which is equal to 1 plus I square minus 2I whole square. We applied a minus b whole square. So we are left with 1 minus 1 because I square is minus 1. So 1 minus 1 minus 2I whole square, which will be equal to minus 2I whole square. So squaring, we get 4I square, and I square equals to minus 1. So this becomes minus 4. So writing minus 4 as minus 4 plus 0i, we get the required form a plus ib, where a is equal to minus 4 and b is equal to 0. Clear? So pause and note down the solution. Next we have question 10. Express the complex number in the form of a plus ib, and the number is minus 2 minus 1 upon 3i whole cube. So taking minus common, we get minus 2 plus 1 upon 3i whole cube. Minus cube is minus, so we are left with minus into 2 plus 1 upon 3 whole cube. So applying the identity of a plus b whole cube, we get 2 cube plus 1 upon 3i whole cube plus 3 into 2 into 1 upon 3i, 2 plus 1 upon 3i. We have used the identity of a plus b whole cube. So which is equal to minus into 8 plus 1 upon 27i cube plus 2i into 2 plus 1 upon 3i. So which is equal to minus 8 plus 1 upon 27i plus 4i plus 2 upon 3i square. Okay, I cube is equal to minus 1. We are going to use that, and I square equals to minus 1 also. So we get minus into 8 minus 1 upon 27i plus 4i minus 2 upon 3. So taking the real and imaginary part together, we get minus into 8 minus 2 upon 3 plus 4 minus 1 upon 27i, which will be equal to minus into 22 upon 3 plus 107 upon 27i. Multiplying by minus, we get minus 22 upon 3 minus 107 upon 27i, which is the required form of a plus ib. Now here we have a is equal to minus 22 upon 3 and b is equal to minus 107 upon 27. Clear? So pause and note down the solution. Moving to question 12. Find the multiplicative inverse of the number under root 5 plus 3i. So multiplicative inverse of z, that is root 5 plus 3i, will be equal to what? Z inverse is 1 upon z. So this is 1 upon root 5 plus 3i. So rationalizing, that is multiplying by root 5 minus 3i upon root 5 minus 3i. We get root 5 minus 3i upon under root 5 square minus 3i whole square, which will be equal to root 5 minus 3i upon 5 minus 9i square. And since I square is minus 1, so we get root 5 minus 3i upon 5 plus 9, that is root 5 minus 3i upon 14. So writing in the standard form, we get root 5 upon 14 minus 3 upon 14 into I. So this is the required multiplicative inverse of the given complex number. So clear? So pause and note down the solution. Moving to question 14. Express the following expression in the form of a plus ib, and the number is 3 plus I root 5 multiplied by 3 minus I root 5 upon root 3 plus root 2i minus root 3 minus I root 2. So in the numerator we have a plus b into a minus b. We get 3 square minus I root 5 whole square upon, and opening the bracket in the denominator, we get root 3 plus root 2i minus root 3 plus 2 root I, which is equal to 9 minus 5i square upon 2 root 2i. And since I square equals to minus 1, so we get 9 plus 5 upon 2 root 2i. Again we have I in the denominator, so rationalizing, so we have to multiply by minus 2i upon minus 2i. We get minus 7 root 2i upon minus 2i square, and since I square equals to minus 1, so we get minus 7 root 2i upon 2. So we writing in the standard form, we get 0 minus 7 root 2 upon 7 root 2 upon 2 into I, which is the required form a plus ib, where a is equal to 0 and b is equal to minus 7 root 2 upon 2. Clear? So pause and note down the solution. With this we end exercise 5.1. I hope I am clear. So solve the remaining sums of the exercise and also the examples given before the exercise. Clear? Bye and all the best.